In Lab 1, we're looking at a system in constant velocity. We will be analyzing the net forces around the system with Newton's first and second laws. Later, we'll be able to compare the system's predicted motion versus the actual observed motion. As you can see here, we analyze the object's motion through tracker. So after using the calibration stick to set the object's length to 5.5 centimeters or 0.055 meters and laying over an x and y axis, we are able to determine the initial conditions. In the video, the object is moving across the positive x-axis to the right. However, for example, if the x-axis was flipped, as the object moved to the right of the screen, the position would become more and more negative. The direction of the object's motion would be indicated by a negative sign. However, the magnitudes of the vectors involved would remain the same as they are now. The mass of the perfume bottle was measured to be 0.363 kilograms. The initial position at time equals 0 seconds was 0.00122100 meters. There was a non-zero y value, but in this problem we are assuming motion in one direction only, so just the x-coordinate is recorded. To find the object's initial velocity, since the velocity equals change in position over change in time, we took the differences of the position and time between the first and second frame to find an initial velocity of 0.63180 meters over second. Finally, we recorded the final time to be 1.033 seconds. This information will be useful to build our prediction model. Newton's second law, change in velocity over change in time is equal to net force over mass, gives us a way to predict future motion. Through this equation, we can measure the total impact of the surroundings of the motion, or in other words, the total interactions of surroundings with the system. Now, in this case, it is important to remember we are choosing this model based on the assumption of Newton's first law. An object will not change its motion unless a force acts on it. That is, the object has constant velocity and therefore zero net forces acting on the system. In order to find the future motion or final velocity of the object, we can manipulate Newton's second law to get this equation. We also need to predict the future position of the object. Average velocity is equal to displacement over change in time. If we manipulate the equation, we can predict the future position, or R final, if we have these values. In this problem, we are estimating that V average is about the same as V final. Now, from the initial conditions we observed, we can make a predicted model of the object's motion through Newton's first and second laws. The predicted model was made from the first and second observations using velocity equals displacement over change in time. As you can see, the final predicted position is a little further out, and the final predicted velocity is a little higher than the actual observed final motion. To explain the predicted results in terms of the fundamental Newton's first law, no net interactions does not mean there are no forces. It just means there is constant velocity without change in direction. Even though the observations can be predicted well by the computational model when net force is set equal to 0, Newton's first and second laws do not tell us how many interactions there are, just that the sum of the interactions is 0. To explain the differences in the observed motion, there could have been factors such as friction slowing down the object, and also movement in the z direction that could explain why the observed does not match the predicted. So an improved prediction model might be one that includes the x and z axis for when the camera is not completely parallel to the object's direction of motion. Moreover, with better methods of recording, there might be a way to make sure the camera is parallel to the object's motion and that the initial force applied to the object to get it moving does not tilt the object's direction.